Thank you very much, Robert, for the introduction. And I would like to thank all the organizers for the invitation for coming here. It's a great pleasure to be at CIUM, first of all, but I'm particularly looking forward to all the discussions we will have over the week. And in this talk, I would like to tell you something about some joint work with Lea Boßmann and Phan. And the topic of what we worked on is to try to understand the dynamics of a Bose gas, so many bosons interacting with each other. And we will consider this situation in 2 dimensions. And what we would like to understand is getting a rigorous derivation of the time evolution for these many particles. And in particular, the key point, which is different to many other works we had seen before, is that we will be working in a regime where we can have a blow-up phenomenon appearing. So that's the main novelty of our work. Okay, but we will go through everything slowly together. So first, for the setting, what we will be interested in is, imagine you have an initial state of, we will have n bosons, n will be a very large number, and in the end we will let n go to infinity. And you imagine having all these bosons, where most of them initially are doing the same thing. So they're behaving in the same way, and I denoted this by having like some small dots or all more or less at the same place. And the question, how would you prepare such a state in experiments is, for instance, you could introduce a trap, and when you have the ground state of a trap system, then you would expect something like that. Now the question we are trying to consider is the following. Imagine you have this nicely prepared ground state, and now let's turn off the trap immediately and ask ourselves what happens for the time evolution of this system. So what do these bosons do for later times? Well, the fact that they are all more or less doing the same thing, you can think of that we work in a regime where the temperature is very low, and the particles are bosons, so they are indeed allowed to do all the same thing. Now, on the mathematical side, the way to describe that, all of them are doing roughly the same thing is to say, if I have an initial particle, you might know that you can describe this using a wave function, where if you take the wave function squared, it gives you the probability distribution of where you expect to find your particle. And now, when I'm saying, they're all more or less doing the same thing, I imagine that they're all, or most of them are in the state phi 0, where phi 0 is some nice wave function. And now the question is, what happens at later times? And experiments from physicists, but also some theoretical considerations, which we will see in the following, show that, you would expect that if, say, most of them are initially in the state phi 0, that at later times, most of them behave like phi of t, where phi of t is a solution to the cubic nonlinear Schrödinger equation, which is the equation you have in the green box. So it's an equation, so phi is a function on, say, R2 or RD in general, and I dt phi is equal to minus Laplace phi plus b times phi squared phi, where this b models the interaction of our bosons. So I said we have interacting bosons, and if the b is positive, it means that the bosons repel each other, so we're in the defocusing case. And if b is negative, it means that the bosons attract each other, which is also called the focusing case. And phi at time 0 is equal to phi 0. So that's the time evolution we would expect. And that's also what experiments show. So at later times, we would expect, again, most of the particles to do the same thing, which is to behave roughly like phi of t. And the main goal we have, and many other people working on similar questions share as well, is to make this understanding rigorous, so to rigorously justify these experimental observations for large particle numbers. We will always let, in the end, the particle number go to infinity. Now, to set up the mathematical framework, I said we will be interested in this system of many particles. So now we need some way to describe them. And here the idea is that we take a wave function that depends on many variables, each of which denotes where the particles are. So we have let me see if we can use the pointer here. So we have psi n of t, it depends on time, and then we have an x1, x2, and so on until xn. So where each of these variables, x1, x2, and so on, describes where you would expect to find the first particle, the second one, and so on. And now this, I will also denote it shortly by just psi n of t. And this is a function that takes variables in r to the dn, so where d is our dimension of the space, physical space, which will be 2 in our case, and n denotes the number of particles. Now I said that we will work with bosons at very low temperature, which means, first of all, that all of the bosons are in principle allowed to do the same thing, so we are in the setting where all the particles can be distributed according to the same distribution, which is very different from fermions, for instance. And also they're indistinguishable, which means that if I exchange, if I ask, well, what's the probability that the first particle is at this place and the second particle is at this place, or the second particle is this place and the first particle is that one, well, that's the same probability. And on the level of the wave function, we have this interchangeability. We have some symmetry in exchanging the positions of two x variables. Okay. Now, for this many particle system, we need some, we need some time evolution. And the time evolution of our many particle system is governed by a high-dimensional Schrödinger equation, which reads as follows. Again, we have some idt of our wave function psi n is equal to hn, where hn is our many particle Hamiltonian, applied to psi n. And psi n at time 0 is our initial state, psi n 0. And for simplicity, you can think of this initial state for now as a product state of the phi 0, which we had on the previous slide. So I denoted it with some tensor product structure, that this corresponds to the setting where literally all the particles at initial time are distributed in the same way. And so now I think, so the way you can think of this tensor product structure is that it's a function psi 0 of x1 times phi 0 of x2, and so on, and you multiply until phi 0 of xn. So that's the function which I denote, of all these variables, that's the one I denote by this tensor product. Okay. Now, I said, well, what I haven't explained yet is this Hamiltonian hn, and that one has a part which involves the kinetic energy and the interaction energy. So there's one typo on the slide, so this little n is in fact a capital N. So think of little n as equal to capital N. So we have the kinetic energy of all the particles, and then we have a part with the interaction energy. So 1 over n, then we sum over all the different pairs, and then I have an interaction potential which I call Wn. Which denotes the interaction of particle I and evaluated at xi minus xj. So you can think of this as the interaction between particle I and particle j. Now here, this Wn is an interaction potential that depends on the number of particles. So this is the regime we want to consider will be a dilute regime. So we want to consider a regime where particles interact just very rarely. And a way to model this is to say, well, I take a fixed potential W, which is an L infinity function with compact support. So you can think of it as a nice CC infinity function, and the precise shape doesn't matter too much in the end for our result. And now we rescale this W. And we rescale it in such a way that it becomes more and more, the support of W becomes smaller and smaller, but we have a prefactor that becomes larger and larger in front. So you can think of this as follows, that the particles interact just if they come very close to each other, but then they interact very strongly. And here, what we will also use later is the following note, just at the very bottom of the slide, is that the L1 norm of Wn and the L1 norm of W are the same. So the rescaling is done in such a way that the L1 norm stays conserved. Okay. Now, next I would like to come back a bit to this, why do we have this nonlinear Schrödinger equation? I had on the first slide, I said, well, it should behave like the solution to the nonlinear Schrödinger equation, but I haven't really explained why. The idea here is as follows. So imagine we are in this initial state, which I had also denoted in the blackboard, where we just have a product state. And let's assume that at later times we're also in a product state. In general, this is completely wrong if the interaction is non-zero. But let's assume it for simplicity. So in some approximate sense, you can still say it's true, and that's something we will justify later on. So let's assume it's in the product state as well, now with a function which I will call un of t. And then if you do some heuristic computations on this n-particle Schrödinger equation you've seen on the previous slide, then you find that the solution un should be a solution to the following Hartree equation, or Hartree type equation, namely that idt un is equal to minus Laplace of un, and now plus an interaction term, which is the convolution of wn with un squared times un, and un at time 0 is equal to the phi 0. So that's the equation you would expect most particles to follow. Now I had told you something about this Wn, which is our interaction potential, namely that it will get more and more singular. And you can think of this as that it converges as a distribution to a delta distribution, or a constant times a delta distribution. And this constant, which I will call b here, is nothing but the integral over w. And now if you formally take this limit of the Hartree equation and you just replace the convolution of Wn with the convolution of this delta distribution times b, then you end up with the cubic NLS, which is the one in the light green box you can see down there, which is also the one we had on the previous slide. So that's the motivation of why we would expect to see a nonlinear Schrödinger equation appear in the limit for very large particle numbers. Okay. So next I would like to comment a bit on the NLS. So far this was all very general and you can do that in any dimension, but in our case we will focus on dimension 2, and the reason is that we have some interesting phenomenon happening in dimension 2 for the NLS. Namely the NLS in dimension 2, the cubic NLS, so where we have a cubic nonlinearity, is mass critical, and it is such that, well, if this B, which models our interaction, depending on the value of b, we can have a very different behavior for large times. So what is important here, and it might be a bit different to what you're used to when you consider the usual literature on NLS, we fix the L2 norm of our initial state phi 0, so it will be equal to 1, because we want to think of the square as a probability distribution, and now it depends on the value of b for the behavior we will see. If it's defocusing, so if b is positive, or it's not too attractive, so b is not too small, namely larger than a certain critical value, then we have a global solution in time, and everything is nice. However, if the b is sufficiently negative, so that means we have a very attractive situation, then we can have initial data so that we have a blow-up in finite time. And in that case, for instance, so it's in the finite time, and we will call this time Tmax. And now, well, and this mass, this critical value has also some, well, is linked to some Galileo-Nuremberg inequality, but let's not go into that detail. So the point is that what we will be interested in mostly is the regime where we can have this blow up. And now you might ask, well, does this even happen? Is this just like some nice trick of some physics that in principle, well, of some math that in principle could happen? Indeed, there are experiments where physicists have tuned this interaction so that it is very attractive, and if it goes beyond a certain threshold, they do indeed see some sort of blow-up phenomenon in the experiment on the many particle level. And what we would like to understand is, well, making this as rigorous as possible, this blow-up phenomenon. Okay.
But you're not telling us that this is the mechanism for the blow-up in the experiment.
So the question was, well, am I telling that this is the blow-up mechanism in experiments? What we will see in the, later on, maybe I just go back before. So what we will see later on is that indeed we will justify that in a certain sense, this NLS is the right, is the right approximation for most of the particles. And we can justify this up until the blow-up time in a certain sense. So if you want, that makes it, I think that's the most you can ask for in terms of plausibility for this blow-up. Does that answer your question? Yeah. Okay, fine, good. Okay, so I would like to come back a bit to the relation between Hartree and NLS. And well, on the left-hand side, we have the Hartree equation, and in fact, you can show that for this one, since we have this smooth convolution, well, this part that we don't have a singular interaction, it is a global solution in time. On the other hand, we have NLS, which can have a finite time blow-up, and in fact there, as we approach the blow-up time, the kinetic energy of our solution phi will go to infinity. And now the question is, how are these two linked? We do know that NLS can blow up, the other one can't. And this is the first lemma we proved together with Nam and Lea, which gives us some precise estimates, which are a very key ingredient from what follows later, on comparing the NLS and the Hartree equation. Namely, if you have some sufficiently nice initial data, say phi 0 is in H4, and you take any time prior to the blow-up time, which I call a capital T, Then there is a constant that only depends on t and phi 0, but not on the particle number n, so that for any time prior to this time capital T, and uniformly in n, you have two estimates, namely that the L2 norm of the difference of the solution to the Hartree equation and the NLS is small in the sense that it's smaller than a constant times n to the minus beta. So we have a quantitative control on that difference. And then secondly, that the gradients, the difference of the gradients is bounded uniformly. Well, now you might say, well, at least until that time capital T, of course it's bounded uniformly. The point is that this is an estimate that is uniform in n, and we will need that later on. Okay, next I would like to come to our main result, and for this I still need some short preparation. So we have already seen the Schrödinger equation on the many particle level. We have seen the Hamiltonian, Hn, in the red box. Now our result will be formulated in terms of one particle density matrices, so which I will call gamma psi n of t. And you can think of them in terms of, if you think of probability theory, you can think of them in terms of a marginal. Here it's a bit more complicated. It's a trace class operator, and the kernel of this trace class operator takes some variables x and y in R2 in this case, and it's defined by integrating over all the other variables. So once you plug in x and all the other variables, once you plug in y and all the other variables, but take a complex conjugate, and then you integrate over these other variables. You might think of just the situation where x is equal to y, then you have a square inside the integral, and gives you the probability distribution of what the first particle is doing, so where the first particle, for instance, is located. But now, if you remember that we have this indistinguishability of particles, if you have information on the first particle, it gives you information on the average of what most particles do. So this one particle density matrix encodes all sorts of information, for instance, if you ask about the average momentum, average position of particles. So it contains a lot of information. Next, we need one other thing, namely some assumption on the initial state. I said you can imagine it as being a product state. Well, like the one I've drawn on the blackboard, that's one option, but in fact we can allow for a bit more. We can allow for some excitations. So the initial state can be in the form that we have our state phi 0, and then with a tensor product with, well, and a sum with some excitations with another phi of k. But what is important here is that we don't have too many excitations. So we have n particles in total, but the number of excitations is bounded. So that's what I've written over there on the right. Well, close it doesn't work. So the number of excitations is bounded, but also their kinetic energy is bounded uniformly in n. So it's a big O of 1 contribution. So it's much smaller than the total number of particles. Okay. Now, under these conditions, what we prove is the following. We show that in dimension 2, for a beta which is between 0 and 3/2, and here you can think of the beta as a parameter that models the diluteness of our Bose gas. So the larger the beta, the more dilute our gas is. And for a phi 0, which is a nice initial state with L2 norm equal to 1, so this describes our condensate, we show that most of, well, and with this assumption on the initial state, we show that in the trace class norm, the one particle density matrix and the projection to the solution to NLS are close, namely, and we can do this quantitatively, namely it's smaller than a constant that only depends on time, times n to the minus alpha, where alpha is an explicit positive constant. So in a way you can say that most of the particles behave like the solution to NLS. Now there are two remarks. What is important here is that we are in a regime where we allow for a regime where we are in the case where it's very focusing. So in particular we can have blow up, so this is just a result until the blow up time. And secondly, we said that the solution to the Hartree equation and to NLS, they are close. So in fact, equivalently to proving the same result for the NLS, you can also prove the result where you take the projection on the Hartree equation, and that's indeed what we will do. Okay, now I have a big slide on the literature, and I would just like to go over it very quickly so that we have time to summarize and for some corollaries. There has been a vast literature in the past on the defocusing case, but also on the focusing case. And well, I won't read all the names to you. What I would like to stress, however, is that compared to all these other results which treat very similar situations. So they treat, for instance, also the case where you have a Bose gas, and where you have, for instance, diluteness. Or you could have the case where you're allowed to have this blow up on the level of NLS, but still you're in a regime where the beta is not too large, so each particle interacts with many, many other particles. In those cases, similar results have been proven in the literature. And in particular, I would like to mention some works by Nam and Napiorkovsky, who have done this in a regime where either the blow-up, where either the parameter beta is not too large, or in the regime where you don't have a blow-up of the NLS. And what we did in our work is we took this as an example, and we try to prove the statement where you are in a dilute regime and you can have blow-up. So in that way, this work is new. Now, coming back to our main result, which is the one you have above, you might ask, well, what about excitations? This is all a result about what most of the particles do. In fact, we can prove a much stronger statement than the one I've presented to you. Namely, we can also tell you precisely what happens with excitations. And this is the following statement. So we have, again, we have our initial state. Let's see if it works now. Yes. We have our initial state with the phi 0, and then some excitations I have over here. And the result is that in the L2 norm sense, we can describe our many particle wave function at later times, again as our time evolved initial state, which will now be evolved according to the Hartree equation, and with some excitations that are modeled according to a Bogoliubov equation. So, which is also a well-described equation. Okay. Now, even from the first result, well, as a corollary, you can show that if you have blow-up in finite time, then you know that for the solution to NLS, the kinetic energy blows up. You have the same for the average particle number. So this is so the average particle has a kinetic energy that goes to infinity. That's something you can prove fairly easily. However, I would like to mention one open question, which I personally find, which I think is among many other questions that you could, for instance, ask for improving the beta. There's one question which I find much more interesting, and it's the following I've written down over there. So for the NLS, we know it's an equation which just makes sense until the blow-up time. So imagine we're in the blow-up regime. Our solutions just stop existing after the blow-up time. However, the solution to our many-body system, well, that's something that exists for all times. And the reason is very simple. It's a linear equation, even though it's in very high dimensions. But for this linear equations, well, the solution, just from spectral theory, is that psi n at later times is e to the minus it hn applied to psi n0. The problem is just that we don't know how to compute this explicitly, but this is something that exists in L2 for all times. So the many-body solution exists for all times, and my question would be, well, what is a good description for this? Or what is going on really? What is a good description for this wave function at later times? And if you have some ideas, I would be very happy to discuss that with you. I will just use 2 minutes to summarize. So what we have been looking at are n particles, where n is a very large number, and these are bosons. And we assume that we're in the setting of Bose-Einstein condensation, which means that most of the particles are behaving in the same way, according to the condensate wave function, say, which at initial time is phi 0. And what we have seen is that, well, prior to some blow-up time of NLS, we can accurately describe what most of the particles are doing by either taking the solution to the Hartree type equation or to the NLS. And what was new about our result is that we could cover the regime where we can have blow-up of the NLS, but we are in a dilute regime. Okay, and with this I would like to thank you for your attention.